Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Vancouver. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE Control Systems Society. Our guest today is Anders Rantzer, Professor in Automatic Control in the Department of Automatic Control at Lund University. Welcome to the show, Anders.
Thank you very much.
So, Anders, obviously it's an honor to have you here with us today. I've enjoyed very much reading about your research in preparing this episode. I found it extremely creative in many different ways. And so I guess I would proceed as we normally do on this episode. So asking you, what has drawn you to control in the first place?
Oh, that's a good question. I would say originally I was drawn into mathematics and I was looking for a university to study this. But I also wasn't sure if math would be my future. So I wanted also a broad base. So I took the program on engineering physics, which is the engineering program which was most mathematically heavy. And once I was in Lund, I got acquainted with a few different departments and subject areas. But control was always an option in Lund for engineering students with an interest in mathematics. Carl Ostrom, who was the professor there and founder of the department, he was always creating a stimulating environment for math-oriented students. So that would be the short answer.
Amazing. So Carl Ostrom has been mentioned multiple times already in this podcast. He's obviously a legend in our field. And in fact, I read from the records that you start then your academic career at Lund quite early during your master thesis, right?
Yes. Doing a master thesis is something everybody has to do in the engineering program. And I was still not sure what I wanted to do, but I asked around and I was already well acquainted with the math department because I had been teaching assistant there for a couple of years already during the engineering studies. And I ended up doing the master thesis under joint supervision from Carl Ostrom and Gunnar Spar, who was in the math department. But finding a subject for the master thesis was non-trivial. So Carl suggested several different topics. I think one of them was already given to many people before, and this was the how to prove properties about auto-tuners for PID controllers using relay feedback. But I didn't think I had a background that would allow me to do anything meaningful there. But at some point he had a visit from Chris Burns. There were lots of international visitors, and he introduced me to Chris Burns, and they came up with a suggestion because there was an introduction of computer programs to solve math problems symbolically at that time. So Maple came later, I think, but there were already a few programs for this purpose. And Chris Burns came up with the idea that I should look into methods to identify invariants under feedback of transfer functions. So if you have a transfer function, you will change it when you introduce feedback, but some properties remain the same. And he wanted to algebraically use symbolic manipulation to compute all the invariants. And then he said that would be a perfect starting point for proving important things about systems. So that was the starting point for my master thesis. But then the direction was changed a few times, and eventually I didn't use any of these symbolic manipulation programs.
Chris Burns is another extremely important figure in our field, or at least I have enormous respect for the work that he has done. And as you mentioned, in reading your master thesis, I did see that one chapter is dedicated to the use of invariants in order to address the question that you were addressing. I guess the opening sentence in your thesis is, what is the complexity of the regulator that we need for stabilization? And I guess complexity here, we mean the smallest order, I suppose.
Yes. This was the question he eventually wanted to solve. And I had also taken some math classes devoted to polynomials and so on. And Lars Amander, who was a legendary mathematician here, he introduced me to a theorem by Tarski-Seidenberg that would essentially prove that it was possible to find polynomials that you could use to check and get an answer to this order, the question about the order. So in principle, we know that there is a polynomial, and if you just put in the value of the coefficients, you will be able to answer the question what order you need of a controller. But from existence to something constructive was extremely hard. The theorem of Tarski-Seidenberg didn't give you any clue about how to proceed. And fairly early on, I was able to find those invariants, but I didn't know where to go from there. And also Chris Burns was gone, and I couldn't ask him for help. So I had to find some other path forward. And eventually I was finding some systems for which I could prove that a reduced order controller could never work. But I wouldn't say I was very excited about it. I thought this will never be of any use in practice. And I think I was a little bit disappointed with the master thesis. But I learned a lot along the way, and that was probably more valuable than any of the results.
Okay, here I have a few comments. So first of all, just to clarify for the audience, I guess one of the main theorems also coming out of this master thesis, which then acts as a springboard, I guess, for your interest in research in automatic control, is about giving upper and lower bounds on the minimal order of a regulator, let's say. And this apparently, based on what I read in the records, also in the preface of your PhD thesis, leads to a paper at CDC in 1987, and then actually also a visit to some research laboratories in the US, particularly I believe in Berkeley, and that seems to have played an important role actually in your future interests.
Yes, this was a very important thing for me to be able to go to a conference and see what was going on in other places. Of course, Lund had a stimulating environment, but these first conference visits really made a big difference to me. And Carl Ostrom was very helpful in organizing visits to a few universities. It's true that Berkeley was an important stop for me, and I got to meet Andy Packard there, for example, who explained also his work on robust control and mu analysis and so on. And it was a very stimulating visit. And the conference also gave me introduction to a number of research topics that were ongoing and didn't seem too far away from what I had learned myself. So that's how I was introduced to this line of research connected to Kharitonov's theorem, which became important during my thesis studies.
Fantastic. Actually, I'm glad that you mentioned that, because I don't think we ever mentioned this particularly cute result in control theory in this podcast before, and this is giving me an opportunity to talk about it. I don't know whether you want to introduce what that is. I can also do the honors as you wish.
Yeah, let me start. So there was a strong interest in dealing with parametric uncertainty during this time. So robust control was a hot topic in the 80s. H-infinity control was, of course, a very hot topic, and many people devoted their efforts to that approach. But it was also recognized that using just the H-infinity norm to describe uncertainty was too conservative for many instances. And this is the reason why people started to ask questions about more specific types of uncertainty. And parametric uncertainty was one of them. If you have systems with real parameters that vary within intervals, it's natural to ask the question, can I find a controller that works for all parameters in these intervals? And it was not obvious how to approach this problem from the start, but Kharitonov's theorem gives a nice contribution to this type of problems, because everybody is using the characteristic polynomial to investigate stability of a system. So the characteristic polynomial has the roots that are the eigenvalues of the system matrix. So if you want to determine stability, you want to make sure that all the roots of these polynomials are in the left half plane in continuous time. And Kharitonov's theorem is dealing with characteristic polynomials where the coefficients are not known exactly, but for each coefficient you have an interval where the coefficients should belong. And if you have then n different coefficients, and for each of the coefficients you have an interval with two endpoints, in principle, if you just would look at the corners, you have already 2 to the n possible combinations. And still, you're not sure that you have covered everything, because it could potentially be that somewhere in the middle of the interval the first coefficient would be. But Kharitonov's theorem tells you that actually you don't have to worry about 2 to the n combinations. It's sufficient with checking stability with just 4 different polynomials. And that will be necessary and sufficient for stability of all combinations of these coefficients. So it was a very cute mathematical theorem that inspired people to ask, how can this be generalized?
An extremely surprising theorem in a way, right? Because you would expect that the number of polynomials, as you say, whose stability you have to be checked is much larger. And in fact, the theorem tells you that you have to do only 4 times as much work with respect to checking the stability of a normal polynomial where you don't have uncertainty of the parameters. And that you can do with the Rauch-Hurwitz criterion, but I guess we're not going to that at the moment. And as you say, this is actually one of the subjects that you pursue in your PhD, right, at KTH?
Yes.
So how did that happen? How did the move from Lund to Stockholm happen?
Yeah, first of all, I was not yet sure whether I wanted to study mathematics and become a mathematician, or whether I wanted to do engineering. So I had been, as I mentioned before, a teaching assistant in the math department, and I was considering this as a possibility for continuation. But at the same time, I've also felt that I was ready to see something new. I had taken most of the courses at Lund University that I found exciting, so I wanted to go somewhere else. And at the same time, I was also coordinating with my girlfriend at the time. So about the same time in 1987 that I finished my engineering degree, I also got married. So we had a 2-body problem. And she was also interested in going to the Stockholm, Uppsala area. Actually, we moved to Uppsala in 1988. So it was an opportunity to see something new, and it was also for other reasons. But also Anders Lindqvist was an interesting person. I met him in Lund, and he was very encouraging, and I knew that he was doing mathematics in the math department, at the same time doing systems theory. So it was a way, maybe you could say, to delay the decision whether to become a mathematician or an engineer. I could do both. So.
I should mention also, maybe as background for our audience, that Anders Lindqvist is also a very influential figure in our field. He worked under Kalman for a period. He's very well known for his work on spectral factorization and stochastic realization. And I suppose that was probably the subject of your PhD thesis, the tentative one at least.
It was the tentative one when I moved there, but I ended up not doing any stochastics whatsoever. And one reason was that I already found this area of robustness to parametric uncertainty before going to Stockholm, and I had some momentum there, I thought, so I just kept doing that.
And it seemed to have worked out very well. This results in a number of papers, as you mentioned, on the subjects that we were mentioning before. So, for example, Hurwitz testing sets for parallel polytopes of polynomials on system and control letters, and several others where you basically deal with the problem of stability in a generalized sense. I was reading about omega stability too. So, for example, having all zeros of a polynomial located in a certain region of the complex plane, and you provide conditions for that to happen, to the best of my knowledge at least.
Yes. So it was various types of extensions of Kharitonov's theorem. I did that quite early on, and then I got invitations to meetings which triggered me for the future. And one of those meetings was in Ascona in Switzerland, where they had made an effort to bring together people from the branch of literature doing extensions of Kharitonov's theorem, and then the other branch of literature which was sort of competing, namely John Doyle's friends and students who were doing who were dealing with similar problems using structured singular values. So that was a very important meeting for me. And I also got to know John Doyle better. Actually, there is more to say about this meeting, but...
Please, if you want to continue, please go ahead.
Actually, then we probably should also take a step back, because there is another person that I think you were planning to bring up later on, namely my contact with Megretski.
Yes.
Because he was entering my world during the PhDs in Stockholm.
Indeed. I mean, I was very curious about that, so maybe we'll talk about it later. In one other meeting that I thought was important, at least based on the records, was this visit to the University of Minnesota, to the Institute for Mathematics and its applications between 92 and 93,
Yes.
if I understand correctly. This was a meeting organized by Hector Sussman, William Fleming, and Jan Willems, all towering figures in our field. And that seems to have been a very stimulating visit for you, right?
Absolutely. But my collaboration with Megretski started earlier, already in Stockholm.
Oh, okay. So maybe we can talk about that then.
Yeah, I think it actually fits now, because I came to Stockholm in 1988. And, in 89, that was the fall of the Berlin Wall. And after that, there was already a lot of things happening in the Soviet Union. And Megretski had done his studies in St. Petersburg with Yakubovich. And he knew very quickly that he wanted to leave the Soviet Union, and he looked for opportunities. But Yakubovich didn't have any contacts to help him. He hadn't been traveling much and so on. But he said, "Oh, you should talk to Nikolsky, the mathematician, famous, for example, for the book on the shift operator, who was also in St. Petersburg." And thanks to Nikolsky, Megretski could be invited for a short visit. I think it was a 3-month visit to the Mitta-Kleffler Institute, which is on the outskirts of Stockholm. That's a math institute which is gathering mathematicians from all over the world around different topics. And Megretski came there for 3 months, and he used those months to make new contacts. And one of the things he did was to ask around, is there anyone who is doing control or systems theory? And he was pointed to Anders Lindqvist, so he came and gave a seminar to our group, and he was talking to people and asked for more contacts because he really wanted to find a way forward outside the Soviet Union. So that was my first encounter with him. But then after 3 months, he had to go back. But then he applied for a postdoc, and he got a postdoc position. So he came back to us and was during my last year as a PhD student, he was there as a postdoc. Then I got to know him, and when I was about to go to this meeting in Ascona, and I mentioned that to him, he said, "Oh, you're going to meet important people like John Doyle. So let me give you a few of my papers and explain them to you so that maybe you can introduce me." So I went to Ascona with a few of Megretski's paper in my bag.
Amazing.
And then I remember sitting at the lunch table and next to John Doyle, and he was explaining to everyone at the table what he thought was the most exciting result of 1991. And he said, it's definitely Jeff Shamma's paper on the multi-loop small gain theorem, showing that if you allow for time-varying uncertainty, then the multi-loop small gain theorem is not conservative. This is so clean result, and it fits perfectly with mu analysis and so on. So John thought this was the result of the year. But I knew I had in my bag the paper by Megretski and Sergei Trail. Those were both young researchers who had been together at... Sergei Trail was a student of Nikolsky, and they had been at the Mita-Kleffler's Institute together. And they had an extremely clean proof of that same result.
No way.
Much cleaner than Jeff Shammas. So I was so happy I could just take the paper out of my bag and impress John, because he didn't know me before and he also didn't know Megretski. So it was a good introduction for both of us.
You got two pigeons with one stone. Amazing. So these results were not known in the Western literature because of the barrier between, let's say, former USSR and the West?
It was quite a recent result. I don't know. I remember exactly the year of the Trail Megretski proof. It was probably about the same time as Jeff Shammas. And it's not... Of course, there was a barrier between East and West, but there was also exchange. Most of the important Russian journals were translated to English. And so even though Yakubovich didn't travel, people were following his work in the West. So I think the IFAC conference has been very important, because the Congress is started in the early 60s and they were running continuously and bringing people together in spite of the fact that the Cold War was going on during all these years. So it's an interesting fact that the academic exchange could be maintained in spite of the Cold War.
Amazing. I mean, also in preparing this episode, I knew that this tension between, let's say, the Russian literature and the Western literature would surface. And I'm glad that you brought up this episode. It's super cool. As a sort of archaeological geek of control theory, I find this very fascinating.
Let me add also that when I speak about Megretski coming to Lund for his postdoc, that the plan, actually his children are the same age as mine, born 89 and 91. So the children were very young. And the plan for him was to start a postdoc in the end of August 91. And he had made flight reservations and everything. And then came the coup against Gorbachev.
Oh my God.
So Gorbachev had been leading the Soviet Union through glasnost and perestroika, and the Soviet Union had been opening up. But of course, there was some people who were not so happy about this, and they had lost Eastern Europe when the Berlin Wall was falling and so on. So many people, when the coup came against Gorbachev, many people got very nervous that the borders would close again. And Alexander Megretski and his family also got very nervous. Maybe our flight ticket is a week away, but maybe it will be too late to leave the country then, because maybe the new government will close the borders. So he decided not to wait that week, but instead put his family on the train through Finland and then the boat to Stockholm.
Wow. Incredible story. Amazing. And as you say, this is an extremely important, I suppose, friendship, but also collaboration, academic collaboration that will lead up to one of the major subjects that you will work on, so integral quadratic constraints that I hope we'll talk about soon. I did read also in the records that you spent a year before returning to Lund in Minnesota, right? And I was
Absolutely
trying to understand what was the role of that year, let's say, in your future career.
Yeah, that was an extremely important year, because this was... In Minnesota, they had this institute called Institute for Mathematics and its Applications. And every year they had a theme. And this year the theme was control theory, 92 to 93. So I would say most of the major players in the field were spending time there. Some of them for a few months, and some of them would just come for a workshop. But it was a fantastic place to stay as a postdoc, because I could just sit there and see the entire world coming through. And John Doyle, I mentioned, I met him in Ascona, and then he told me he would be in Minneapolis. Actually, he had been in Minneapolis regularly. He had an apartment there because he was at Honeywell in parallel while doing his PhD. So he still maintained his contacts with Honeywell, and he had an apartment in Minneapolis. So he was staying there for several months. I don't remember exactly how long. Jan Willems was there. Trifon Giorgio was there. I mean, obviously, Trifon was a faculty member in Minneapolis for many years, but it's actually hard to say anyone who was not there during that year. But I think Megretski was not there so much because he was spending the time in Australia. After the postdoc in Stockholm, he was 1 year in Australia before coming to Iowa in Ames. But definitely it was a year that shaped my picture of the field entirely. And I also learned a lot by the IMA organization. So eventually, being back in Lund, I tried to copy many of the ideas for running guest programs. So we have been running similar programs to bring people to Lund in a systematic way.
I was lucky enough to participate to one of those extremely interesting at the Linnaeus Center, I believe you're referring to.
Yes.
Incredibly interesting, at least the one that I did participate to on sensory motor control. Fantastic lineup of superstars, not only from control theory, but also from neighboring areas. And I thought that would actually generate a lot of value because it would bring up problems and ideas coming from different fields, which is always refreshing. And then I see that, at least in the records, that after this year at University of Minnesota and the IMA, there's a paper where you also are one of the authors, together with, as you mentioned, John Doyle and many others, including Bo Bernhardsson, titled A Formula for the Computation of the Real Stability Radius, that somehow brings together the expertise that you had developed until then to work on also some of the other tools that we were mentioning before, so mu analysis, and in particular here, I guess, the real stability radius. Shall we talk about that briefly, or?
Yeah, we can do so. So we were 3 postdocs sharing an office, and it was me and Bo Bernhardsson, who was actually a longtime friend of mine. I got to know him when we were 18 and doing high school competitions in mathematics. but then it was Li Chu from Hong Kong. Li had been doing his PhD in Canada with Ted Davison, and he had already started to work on this problem. So the literature around the structured singular value was interesting because there were a long sequence of papers dealing with different assumptions on the structure of the uncertainty. And some of them led to very clean results, and for others, there was just computational algorithms that you never knew actually what they would give you. But this was one of the instances where you could get a very clean and exact answer. And this was the problem when you had just one uncertainty block, but this extra structure that made it different from the H-infinity control was that the perturbation to the system matrix was real. So the exact problem is, given a matrix with eigenvalues inside the left half plane, so it's a stable one, what is the smallest norm of another matrix with real coefficients that will make the sum of the two unstable? So it's a very clean mathematical problem, but it turns out that it's much easier to solve it if you allow the perturbation matrix to be complex, because then you can answer the question very easily with just the spectral norm or the largest singular value. Because the reason why complex numbers enter the picture is that sometimes the eigenvalues are escaping on somewhere on the imaginary axis other than 0. So that's why complex perturbations enter the picture and complex matrices enter the picture. But this problem was already brought to our office by Li Chu, and he had some preliminary results from Ted Davison. And if I remember right, there was already a conjecture about what the answer should be. But there were some missing pieces, and during this time together in the office, we were able to sort out those missing pieces. Then there were 3 more authors I think it was Ted Davison, John Doyle, and Pete Young, who had been taking part at previous stages of this development.
It's a very good result, as you say. Basically allows you to calculate this real stability radius via essentially bisection or like golden section search, let's say, because this function that you're optimizing also is unimodal, so you know that you're going to find the value of this function essentially very efficiently. If I can make a brief summary out of this, I hope.
Yeah, actually, maybe you should remember that even computing the H-infinity norm of a transfer functions involves bisection. So having bisection in the picture is not unique in any way.
Yeah. Okay, so generally, somehow, so this draws you, I guess, to the question of robustness. And I'm glad that you also mentioned the interaction with Alexander Megretski, because then I see, at least in the records, that you gradually work your way towards this paper on integral quadratic constraints that I'd like to talk about. There seems to be a preliminary paper before that called a convex parametrization of robustly stabilizing controllers. That seems to be a prequel to that. I'm not sure whether that could be thought as a prequel.
No, I think that's quite separate. I would say the paper that you're referring to is something I did with Megretski in Stockholm.
Okay.
And this is still in the context of real parameters perturbing the system.
Okay.
Whereas actually it was an interesting time at IMA 92-93 because it was sort of marking the end of robust control. I have heard Munzer Dahle say that the Riccati equation solution to H-infinity is the worst that could happen to robust control. It sort of killed the field. And I think John thinks the same, but with other motivations. But you could feel in the 92-93 that robust control was more or less over, but everybody was asking, what's next for our field? What should we do now? And also at conferences, things changed. During the 80s, there had been very clean and clear problem formulations that people could gather around in the H-infinity literature. It was very exciting because mathematicians and engineers came together in a very fruitful way. But in the 90s, the mood was changing. And during that year in 92-93, I sort of got to know the broad picture of the field, but I also got this feeling that many people were hesitating about where to go next. And one of the things that were not yet sorted out was how to handle structure in the uncertainty when there were nonlinearities involved. Of course, there was a literature back in the 60s and 70s on Same's work on the small gain theorem and Wilhelm's work on dissipativity theory, and that allowed you to handle nonlinear perturbations to a system. But then there was the work on structured singular values that was completely focused on linear time invariant perturbations. And there was still not a common framework that would allow you to treat dissipativity together with structured singular values. And this was a missing thing, and this is a challenge that was very exciting.
I can imagine. And this results in, well, the birth of the IQC paper that I'm so eager to talk about, I guess. It's published on the IEEE Transactions on Automatic Control in 1997. It's a jewel that I recommend to every listener of this podcast. It's really, I'm going to say like my personal opinion, but it's really one of those papers that you should read, that everybody in our field should read.
I should add there that actually most of the ideas were already in Alexander Megretski's notes, even before I got to know him. I saw a draft from Newcastle during the year where he was after the postdoc at KTH, and he fleshed out much of the IQC approach. But there was a missing piece, and this was the homotopy argument that became the centerpiece eventually to bring together the nonlinear literature with the linear time invariant literature. And I can't, also that idea was Sasha's actually. So it's hard to know actually what role I played, except for doing much of the writing. But I guess whereas Sasha was always fast and brilliant, I was persistent. So I kept coming back to those unsolved issues, and eventually I got him to solve those as well.
So first of all, there's a lot of meat on the grill here because there's several traditions coming together in a single paper, as you mentioned. So connections to, I would say, the most, well, not disparate, but let's say long-standing traditions, both in the Russian literature and in the Western literature, as you mentioned, let's say the theory of multipliers, but also dissipativity theory developed by Jan Willems. In fact, this is already in the abstract. There's a sentence where you say, from an original idea by Yakubovich, the approach has been developed under a combination of influences from the Western and Russian traditions of control theory. And I should also mention that that was also an important time because linear matrix inequalities started to play a very important role in our field because they could be solved very efficiently. So how do we organize our discussion around this paper?
I don't know, but since you mentioned the LMIs, I have to go back again to an interesting event when I was a PhD student in Stockholm, because this was the division called the Division of Optimization and Systems Theory. So there were a few people like myself and Anders Lindqvist who were focused on systems, but there were also optimization people. And they were inviting interesting guests as well. So at one instance, we had Nesterov and Nestorovsky there, and who had just published their seminal work on polynomial time algorithms for semi-definite programming. It was fantastic to hear their presentation, and they were optimization guys. They didn't have much idea what we were doing in systems theory, but I could see immediately that we had a field full of those linear matrix inequalities that needed a tool like that. Unfortunately, I was too occupied with Kharitonov's theorem and so on to actually take advantage of the opportunity, but I could really see the potential. And then not so long after that, Stephen Boyd and his collaborators wrote the LMI book published by SIAM.
In fact, in preparing this episode, I went back to looking at the year of the publication of these two books that we are implicitly referring to. So one is the one by Nesterov and Nemirovsky, Interior Point Polynomial Methods in Convex Programming. There will be a link in the description, 1993, published on SIAM. And then also the other book by Stephen Boyd, Elgawi, Eric Ferron, and Balakrishnan, Linear Matrix Inequalities in Systems and Control Theory in 1994, also published by SIAM. So we're really navigating around those years. I thought that maybe to flesh out a bit more the subject of integral quadratic constraints, we should actually define what is an integral quadratic constraint.
Yes, so we usually state the integral quadratic constraints in frequency domain. So if you have an operator relating inputs and outputs, assuming that, let's say you have an operator with bounded gain, so you feed it with an L2 bounded input, you will get an L2 bounded output. And then you could look at the Laplace transform or Fourier transform of those signals, and you can state a quadratic expression, a quadratic form in those input-output variables in frequency domain. And the weighting matrix of those quadratic forms is very important, because you can characterize the operator by saying that the input-output of that operator will always give you a non-negative value of the quadratic form defined by the frequency weight matrix. And the more better understanding you have of your operator, the more quadratic forms you can define in this way and which give valid inequalities. So a typical example would be a time delay, which is something which is tricky to handle in continuous time because you get an infinite dimensional system when you have a time delay. And if you add to that there's an uncertainty in the time delay, it's hard to quantify such a description or such an object in other ways. You have an infinite dimensional object and it's uncertain. So how do you handle that? But it turns out that if you just say, okay, this is a time delay and it's limited, the time delay is limited to an interval, then you can derive a lot of quadratic forms in frequency domain that are valid and that are only valid when the delay remains in this interval that you assume that your time delay should be. So that's just one example, but there are many other things. We proved integral quadratic constraints for hysteresis, for friction, even complex friction models where you have more way of stiction. So when things don't move, you have more friction than when they start moving. And you can quantify the level of stiction in terms of integral quadratic constraints. So it turned out to be a very versatile tool, and you could use it both for nonlinear objects and for real parameters that were previously treated using structured singular values.
I have a lot of comments. Well, I'm a big fan of this paper. I spent quite some time also reading it, and also the technical reports associated to it, where you also characterize, as you say, multiple types of quote-unquote troublesome blocks, such as delays, but also many others. There's two comments. So first of all, one is the history of what are integral quadratic constraints. So I think it would be nice to clarify also to our audience the tradition that comes from absolute stability theory, all the way from Eisenman to Popov, Yakubovich, and also the reason why these IQCs are tractable. And I guess here we have to talk about also the KYP lemma as well.
Yes, as you are pointing out, there is a long history, and just notions like passivity and gain bounds are examples of constraints that fit into this framework, but which have a much older and longer history. I think already Yakubovich used the term integral quadratic constraints. Actually, we were quite hesitative about our paper because we were not sure that there was anything new in it. Because there had been so many branches of literature that had been touching on this subject. So I even have in my desk a note from Megretski with the title, "Is there anything new in the paper on integral quadratic constraints?" And discussing the relationship to Yakubovich's work. Because Yakubovich really published a long sequence of papers which relates to this.
I'll clarify maybe to our audience that essentially what is absolute stability theory, where does it start? I think we can trace it back maybe to the 60s or even 50s.
Yeah, even 50s. There is this Laurier problem, which is often used in textbooks to introduce this problem. It's an interconnection between a linear transfer function and a static nonlinearity bounded by a cone condition.
And the question is, when is that stable?
Eventually, this led to the circle criterion and Popov criterion, but before that, there were a number of conjectures that were given by famous people like Eisenman and Kalman and so on, but eventually it turned out to be wrong.
Yeah. And at the same time, as we were mentioning also, the reason why integral quadratic constraints are not only flexible but also tractable is that we can turn conditions expressed in the frequency domain through integral quadratic constraints to conditions that can be actually tested and verified through the solution of linear matrix inequalities, right?
Yes, and this was also a sort of paradigm shift, because already in the 1960s, people had been specifying these linear matrix inequality as important, but they didn't have a way to solve them. they didn't have the Nesterov-Nemirovsky machinery to solve semi-definite programs. So then they came up with the Kalman-Yakubovich Popov lemma to turn this matrix inequality into a frequency condition that allowed them to just make a plot in the complex plane and check it easily. So, and now we started to go the other way around because we had the powerful tools for solving semi-definite programs. So we were using the Kalman-Yakubovich lemma in the other direction, where frequency condition, which was much too complicated to be illustrated in a simple Nyquist plot because we were having multivariable systems. And then the plot is far from trivial, even to draw, and even more difficult to use for anything. But then you can use the KYP lemma to bring it into a linear matrix inequality, and then there was this optimization framework to solve it that made it tractable.
And I guess the Kalman-Yakubovich Popov lemma would deserve an episode on its own, also for its fascinating history. But as you say, like one could combine multiple IQCs together and then just feed it basically algorithmically to a solver and just test whether numerically, whether an interconnection is stable. Actually, this gives me another segue onto another paper that basically surfaces around the same years, more or less, on the Kalman-Yakubovich Popov lemma, also written by you as a single author. Do you think, is that a good time to talk about that too?
Yeah, we can do that. Actually, before I go into that, let me just mention my first meeting with Yakubovich, because...
Oh, wow.
because that was interesting. As I told you, Yakubovich didn't travel much. So to meet with him, you needed to go to St. Petersburg. And after I finished my PhD thesis in Stockholm on the Kharitonov theorem, I got a letter from Kharitonov.
Wow.
So he was a professor in the math department in St. Petersburg. And he wrote a very nice letter to me saying, I learned that you have been writing a thesis with extensions to my theorem. Why don't you come to St. Petersburg? I'd be happy to host you.
Amazing.
So I saw the opportunity. Of course, I said yes immediately. And I was staying with him in his apartment, and he served me vodka for the breakfast and everything that you expect from your first visit to Russia. But then he said also, I have a neighbor that you should meet. In the next building, Yakubovich lives, and he wants to invite you for dinner. So apparently, even though he didn't travel to meet people, he was happy to meet people who came to visit. So I had a dinner with Yakubovich and one other person. Actually, it was a very old man, like more than 90 years old. And I was told that it was only the three of us. Yakubovich, I don't know about Yakubovich's wife, why she wasn't there, but apparently the old man was her father. So it was Yakubovich's father-in-law.
Okay.
And he was a very interesting person because he had been serving as a secretary or something like that for Kolchak, one of the last generals that was fighting the Bolsheviks in 1917 or something like that. And this had been a secret, so it had been dangerous for him to tell anyone his experiences, because communists were looking for people that had this background. But he had been only very recently able to tell people about this secret. So it was really a historical moment that was going on.
Amazing. And one question, could you speak Russian or did you?
No. So I could talk to Yakubovich in English. I don't know how come he had learned English given that he didn't travel, but he was able to help out with the conversation.
Amazing. And did you ever talk about also integral quadratic constraints? Or
we did talk about the Kalman-Yakubovich Popov lemma. That I remember clearly because I had a way to state it that he was not very comfortable with, I think. One thing that happened in the early 90s was that Andy Packard found an LMI solution to H infinity. And that was an interesting paper. for me to read, obviously. And he was heavily using Yakubovich Popov lemma in a way that I could understand, and this is what I was bringing with me, and it was very different from what Yakubovich was used to. And later on, Alexander Megretski told me that actually I should do it in a different way. It was too limiting to just stay with Andy Packard's version, which was perfectly fine for his purposes, but not for the IQC papers and so on.
And so is that how your interest in the KYP lemma originate?
Yeah, I got interested because I understood that this was a useful thing and it was non-trivial to prove. But then there was this paper by Andy Packard and John Doyle saying in a footnote that one of the ideas that they were explaining in this paper on complex structure singular values, that it would be possible to use it to prove the KYP lemma. But they didn't show how. And so if you look in my paper on the Yakubovich Popov lemma, I say there that this is really just my way of working out the remark from Andy Packard and John Doyle in their earlier paper.
And so there you have a one-line abstract, well, two-line, where you say the purpose of this note is to present a new elementary proof for the multivariable KYP lemma. A minimum of linear algebra and finite dimensional convexity theory is used.
Yes.
I can say that I did read the paper more than once, actually, and it took me maybe more than one day to digest, if I have to be honest. But it's an extremely elegant paper, only 4 pages, and strongly recommended to the audience. Obviously, there will be a link in the description.
Okay, so the fact that we use elementary math maybe makes it even harder to read. I don't know. But I'm very impressed by the way you prepared for the podcast.
Thanks. It's to satisfy actually my own curiosity in many different ways. The paper is actually one of the most cited of your papers, so it ended up to be a very important footnote that you read and worked out.
Yeah, I remember you asked me when we prepared if I have any advice for students today. Maybe that's a good advice, to take interesting papers, read the remarks that people make about unfinished directions, and then work from there.
Because they may lead to some important results. So chronologically, now we're proceeding not only thematically, but also chronologically. I guess here now we're approaching the years 2000s, more or less.
That's right.
You've become now a professor at the University of Lund. And as you say, also the trends in control change. And it seems like this is the age where nonlinear and hybrid systems really take the main stage in our field. And it seems like you do have, again, very original ideas also in this regard. One paper that I found particularly interesting is the one on piecewise quadratic Lyapunov functions. I guess at the time it was even difficult to define what a hybrid system was. And there were a whole host of different approaches to dealing with classical problems such as stability. And maybe you can tell us a bit more about this approach.
Yes, I mean, clearly, as I mentioned before, after robust control was basically finished, people started to look for other important directions. And during the 90s, I think the main defining theme of that decade was the use of semi-definite programming in control. It allowed people to solve new problems by restating them into a format that could be dealt with these optimization methods. So that was the background. Now we are approaching the end of the 90s, and I think it was Shankar Sastry at Berkeley who was pioneering the literature on hybrid systems, because he saw that there is all sorts of problems where we have to deal with computer science in combination with control literature. And computer science literature is typically developed in a discrete setting. And when you tie things up to control, which is often done in a continuous setting, you have difficulties. And so, inspired by these challenges, people try different ways of doing this. And actually the idea of studying piecewise linear systems and piecewise quadratic Lyapunov functions was not mine, but it came from Mikael Johansson, the PhD student in Lund that I worked with. Together we could turn these problems into the optimization setting and solve them using linear matrix inequalities, which is a tool that I had by that time used a lot, and so I knew how to use it.
And as you say, there's a number of papers working out this approach together with Mikael Johansson, who's now a professor at KTH Stockholm. So you deal with different classes of systems, but generally piecewise affine. So one partitions the state space in different regions, whereby hopefully one can characterize those regions in terms of piecewise affine dynamics. And then through the use of Lyapunov functions, I'm not sure whether I'm allowed to call them this way, I guess so, but discontinuous Lyapunov functions across different partitions of the state space, one essentially is able to prove stability. This is the gist, as much as I understand from reading those papers, by turning these stability problems into the solution of linear matrix inequalities.
Yes, that's true. But very often the difficulty comes when you start to ask, how should I split my state space to get the surfaces where the quadratic functions should be pieced together? And that's a challenge that we were never really able to sort out.
That would have been actually my main question. So in a sense, also it's a manifestation of the curse of dimensionality somehow, right?
Yes, you could say so. But I think, as is often the case, when you encounter difficulties, you change direction, but you have learned something along the way that turns out to be useful also later. And in this case, proving stability using a piecewise quadratic Lyapunov function was one thing. We had a paper on that. But the next question was, how do we design controllers? And analysis is one thing, but when you go to synthesis, things often becomes much more complicated. I don't remember exactly how we came up with the idea, but there is an old idea in optimal control that if you replace the Bellman equation by an inequality, then you can at least get lower bounds on the optimal cost. And if your lower bounds are accurate enough, you can also use them to design close to optimal controllers. Actually, I think this came from the LMI book, because in the LMI book by Boyd and co-workers, there is treatment of synthesis, and the Bellman inequality comes up in this context. And now we had these piecewise linear systems, and we simply wanted to generalize this to more complex systems. And then we looked again at the same Bellman inequality. And this approach has been extremely valuable for me until this day. I'm still doing things where I come back to the Bellman inequality and the lower bounds on the optimal cost that you can obtain this way. So several of the papers I wrote around that time are based on this idea.
I'm glad that you mentioned also your research interest on the Bellman equation. I'm sure that we'll go back to it later in the episode. It's certainly something that I want to talk about. Maybe I'll briefly mention also for our audience that the ideas that you were mentioning just now about optimal control and the Bellman equation can be found in a publication that is titled Piecewise Linear Quadratic Optimal Control, another little jewel, in my opinion, published in 2000, again with Mikael Johansson. Strongly recommended to the audience. There will be a link in the description. I feel that I'm galloping through this phase of your career, not to do injustice to it, but because there are several interesting results, or at least results that I found particularly interesting. One of them we actually did talk about before in this podcast, fast switches in relay feedback systems. So you actually went back to the relay problem with Kalle Johansson, who was also on the podcast recently. And another really beautiful theorem about, well, titled A Dual to Lyapunov's Stability Theorem. I definitely want to talk about this. So I don't know, what's your preference actually?
Yeah, we can talk about this paper that you mentioned most recently, the dual to Lyapunov stability, because it actually grew out of the work that we did on the hybrid systems. When you are dealing with hybrid systems, it's natural to look at how things work out in the discrete setting and then the continuous setting, and then see if you can transfer ideas from one to the other. And if you look into the discrete setting, the problems that correspond to optimal control are shortest path problems in graphs. So the state space is now a set of nodes in a graph, and the cost is associated with jumping from one to a node to another. And these problems you could solve using linear programming. And linear programming always has a dual linear program. So in the discrete setting, there is a very natural primal dual combination. And in one of the instances, the thing you optimize is the cost, what corresponds to the Lyapunov function. And if you take the dual, it's instead some flow variable or density variable. So I found it completely shocking to see how this was done routinely in the discrete setting, but in the continuous setting, I didn't know what the dual would be to the Lyapunov function yet. So I simply had to work out the correspondence between the continuous and discrete world. And so in a sense, even if we didn't solve many hybrid control problems, just the fact that this literature was encouraging looking into computer science and control in parallel and see what ideas are common was very fruitful.
Fantastic. Again, this is a must read in my opinion. It's a very original and creative result that somehow is a dual, as we will explain also soon, to Lyapunov's second or direct theorem, which is the usual theorem that allows us basically to prove, let's say in its simplest form, global asymptotic stability of an equilibrium by finding continuously differentiable Lyapunov function, so a function that is 0 at 0, positive everywhere else, and such that its derivative is negative except at the origin. And this is a very powerful result because it allows us to say something about the stability of a system without actually solving the differential equation. And I guess at the beginning I found it difficult to understand what you meant by dual, but then, as you say, it's very clear as you read the paper that duality in this sense inspired by the duality that one finds in optimization. In fact, also one thing that you also mentioned, that you said that it was surprising for you to see that this result was not developed. This is also in the introduction of your paper. There is a section where you say it is surprising to find that Lyapunov's theorem as a close relative presented here as theorem 1 that has been neglected until the present date. I was thinking that maybe we can give some sort of physical intuition maybe to the audience about the result that you actually present in this paper. The way I see it is essentially a density function flowing along trajectories, and the idea is that if this substance concentrates only near the origin, then convergence follows. Is that a good intuition?
Yeah, the way I would present it is usually think of a situation where you produce new substance everywhere in the state space.
Mm-hmm.
And at the same time, we have an assumption saying that the amount of substance is limited as you approach infinity. So the substance that you produce cannot just move away towards infinity. And then the only place where the substance can go is towards a singularity in the density, some place where the density is infinite. And if there is only one point where you have such a singularity, then almost all trajectories have to go there. It's important to say almost all because there could be a set of zero measure that goes elsewhere. So this makes it different from the Lyapunov theory, which really requires that all trajectories go to the equilibrium. Here, the conclusion is weaker. The conclusion is that almost all trajectory should go to the equilibrium. And the distinction is sometimes important because there are systems where a small set of trajectories go somewhere else. For example, if you have a pendulum, it has an equilibrium downwards and it has an equilibrium upwards. And for almost all initial conditions, the pendulum will go to the downwards equilibrium because that's the stable one. But there are also some trajectories that end up in the upright, unstable equilibrium, and they are of zero measure, but they prevent the existence of a Lyapunov function, which is global for the pendulum. But with these density functions, you can still get certificates in this way.
It's very fascinating, and also the interpretation of the Lyapunov function as a cost to go. Of course, there are connections between, let's say, optimal control and dissipativity, and therefore also Lyapunov functions. But I didn't see, before reading this paper, connections also to linear programming being so explicit.
I mean, there are definitely authors in the past who have been emphasizing this, but still when you are trying to prove a result about stability in a continuous state space, it's not so easy to find those papers because maybe they are dealing with a stochastic setting in a finite state space. So even though the ideas are there, and certainly the linear programming approach to optimal control is not new, but it hadn't been used in this way before.
And now I have basically a curiosity more, or a personal question that also maybe gives us a segue towards another chapter of your research career that's on the subject of positive systems. Was it actually your endeavors on research on linear programming guiding you towards that?
No, I wouldn't say so.
So what has drawn you? Because I see clearly that at some point your focus changes and starts to look at positive systems and monotonicity at large.
Yeah, so again, I'm inclined to look at the history of our field decade by decade. So if the 90s was the decade when people were taking advantage of optimization methods seriously, the next decade was really where the large-scale systems came into as a major challenge for our field. There were some papers around the millennium shift devoted to internet congestion control that I found very inspiring. And then I was at Caltech for a sabbatical in 2004 and 5, and I was even more exposed to all the challenges related to scalability. And you can also see that in optimization literature. In the 90s, people were making everything into an LMI, and they could solve it with polynomial time methods. But nowadays, there is much more focus on first-order methods than the second-order methods that Nesterov and Nemirovsky used to deal with linear matrix inequality. And the reason is scalability. The first-order methods don't have the complexity issues that come up when you are computing the Hessian. So when people started to look into large-scale systems, there was again a period when different groups came up with different approaches, and it was not clear which approach would be the dominating in the end. There was an interesting path of literature where people looked into distributed controllers. So instead of having a feedback matrix which was full, you looked for sparse controllers, and people were asking when can, for a sparse system, the search for a sparse controller be turned into a convex optimization problem. So there was the work by Sanjay Lal and Mike Rotkovitz, for example, in this area. But even though people were able to find problems where you could get sparsity and optimize sparse controllers, the outcome would be very complex. And even though you could state it as a convex optimization problem, the convex optimization would be very complex and it wouldn't scale well with the number of nodes or the size of the matrices and so on. So you would get convexity, but you would not get scalability. Then at some point, I ran into a paper by Takashi Tanaka, who was a PhD student of Cedric Langbort in Illinois, where they used positive systems theory to show that you could, instead of solving LMIs with full matrices, you could solve with diagonal matrices. And that was really a breakthrough moment for me. I was thinking, wow, I have to learn more about these positive systems. And since then, I've been working on that topic. And it's almost 20 years ago now, I guess.
I mean, you're still active, as you say. I think it's quite hard actually to do justice to the body of literature that you've produced on the subject. I'll refer maybe the audience. There's an ECC plenary that you gave, luckily, on YouTube in 2015, I believe, on scalable control of positive systems that gives a very nice overview of your work there. Obviously, until that time, a lot has also been developed also in recent years. I guess maybe one question that I could ask and that will allow us also to explain to the audience why this is relevant. What does positivity buy you, in a sense?
Yeah, so that has a very simple answer. So if you have a positive system of order n and want to prove stability, you can do that with linear Lyapunov functions rather than a quadratic one, which means that the number of parameters will also be n, whereas in the quadratic Lyapunov function, the number of parameters grows with the square of the number of states. So you have linear dependence on the number of states rather than quadratic. That's the whole difference, and it's quite fundamental.
I found this obviously very cool. Maybe I can mention also briefly what is actually a positive system. I don't really remember whether we mentioned this before. I believe so, but just for the sake of clarity, also for our audience, a positive system, okay, depending on whether we talk about a system that has inputs and outputs. So if the system is autonomous and has no inputs and outputs and is described by, say, a state space description, then we're saying essentially that starting from non-negative initial conditions, I will continue to have, the trajectory will always be non-negative. And this idea can be generalized in many ways. It is deeply connected to very fundamental results in matrix theory, namely Perron-Frobenius theorem, one among many. Okay, and then I think it's probably important to mention what are the consequences of this scalability, both for verification and synthesis, I believe.
Yeah, I think much of what we do in systems theory is to analyze systems, prove important properties about them, and to design controllers to improve such properties. And for both analysis and design, the scalability is crucial if you are dealing with large systems.
Yes, and one more thing that I would like to add maybe to this subject is that there's plenty of examples out there of systems that can be described by positive systems. I'm thinking of energy grids, traffic networks, or anything where non-negativity represents essentially the fact that something like a density, for example, cannot be negative.
Yeah, biology is full of positive systems models. Actually, now we are moving beyond positive systems and look into more general notions of positivity, namely that the state should be restricted to a cone. So for a standard positive system, the cone would be the positive orthant. But if you are dealing with traditional linear quadratic theory, the cone would be the set of positive definite matrices. And so if you look at how the Gaussian stochastic distribution, it's represented by a covariance matrix with a constraint that it has to be positive semi-definite. It has been very rewarding to bring different types of cones into the same framework. Sometimes it is the orthant, sometimes it's the set of positive definite matrices, but there are also many other types of cones that, like a second order cone is common in convex programming. That is a cone defined by a second order inequality. But also when you are dealing with systems with graph structure, saying that some nodes are connected, others are not. You want to deal with sparsity. This can also be brought into the cone structure. So for someone interested in mathematical systems theory, I think it's a very rich set of results and very rich sets of problems that can be addressed in the context of systems on positive cones.
I found this subject very fascinating. I mean, there's many things that we can say about this. For example, the notion of positive dominance that you've also studied in depth. So essentially a frequency domain analogues of the notion of positivity or variations thereof. I will refer actually the audience to some of the papers that actually illustrate these ideas. As I mentioned, the Scalable Control of Positive Systems, that is a publication associated to your ECC plenary in 2015. Also a CDC tutorial that you've written in collaboration with Maria-Elena Walker as well. A recent paper with Richard Pates on optimal control on positive cones. These are some of the many. But I'm mindful of time, and I really want to talk about also some of your latest endeavors that I find particularly interesting on adaptive and dual control. Also using covariances and basically going back also to what we mentioned before about Bellman operators.
Yes, I've been... Okay, if now we're entering into yet another decade, and if the first decade after the millennium shift was the decade of scalability, I think the next one was dominated by the tools from machine learning and their interaction with control. So obviously the dual control problem is a very old one. It goes back to 1950s or 60s. And adaptive control was always at the center of Carl Åström's activities in Lund, as long as I can remember, and actually quite a bit before my time as well. So doing learning for control is something people have been doing for a long time, but I think for many different reasons, it's really more worthwhile to come back to this problem again. One is, of course, the new tools that we get from the machine learning and AI explosion, but also that is very rewarding to look at again at the interface between the discrete and continuous world when you start to apply these methods for the purpose of control. So I've been in the last few years teaching a course on learning-based control based on a book by Betzekas. And I found it very rewarding for myself personally because, of course, Betzekas knows the subject of optimal control and dynamic programming by heart since his early years as a PhD student. And he has been writing all the main references in the literature on dynamic programming and optimal control. But what was making his book useful for me was that he was using control notation and control language while dealing with reinforcement learning problems that are otherwise treated in quite a different language. And the language is important because the language helps us understand what is at the core of the ideas. And it's also very helpful. I mentioned already that I've been working with dynamic programming and Bellman inequality, and now I can come back and use this tool in the context where learning meets control. And I think it's very exciting.
Indeed, and this is actually reflected in the plenary that you gave in 2023 at CDC, also available on YouTube, I believe. So there will be a link in the description, strongly recommended. And it hinges basically on, to the best of how I can describe it, on a new parametrization, if you want, that seems to be very fundamental of a covariance parametrization, somehow that you call the data-driven Riccati equation, or that originates from a data-driven Riccati equation, if I am correct.
Yes, it's true. At the same time, I should say that even though this was a very exciting result to discuss at the plenary, I think the most exciting things are yet to come. Because now we are seeing that the Bellman equation actually have analytical explicit solutions in some of these instances. It's very rare that you can solve the Bellman equation exactly, but it looks like that many of the core problems in dual control can be treated based on explicit solutions of the Bellman equation. So I'm very excited about this.
I should mention maybe two things again for our audience. So there is a whole episode that we did about Bellman, and the Bellman equation is just something that is related to how do you solve optimal control problems, basically through dynamic programming. And as you mentioned, in some cases, this equation actually has explicit solutions. And this is surprising because it is, in principle, a functional equation, right? So something that is, in general, quite hard to solve. So what are the consequences now of some of the results that you're developing?
Yeah, I think, so there is this exploration-exploitation trade-off, which comes up all the time when you do learning for control. Actually, I can use an example that I recently used in a proposal together with some cancer researchers, because they are treating cancer patients with immunotherapy. And sometimes it works, sometimes it doesn't. And nobody really understands the mechanism behind it. But what is clear is that there's a need to individualize the treatment. So to some extent, they can do this by taking a DNA sample from the patient and then look at the genome and see how does it match the historical data we have from other patients. Is this patient likely to respond in a certain way based on the massive amount of data that we have collected before? So based on this DNA test, they can make a individualized prediction of the response to the treatment before they even start. That's like feed forward in a control setting. You make a plan for the therapy before you even start, just like you plan the trajectory of a rocket that you want to send to the moon. But then once you start treating the patient, you want to learn from the response that you see, and then the data points will be very few. You get a blood sample every third week or something like that. And the machine learning literature is full of examples of success when you have lots of data. But here you have a situation with very few data points, and you have to make a decision that could mean life or death of this patient based on these very few data points. So I think this is where control expertise really can be useful to complement the big data literature of machine learning. And it also has this exploration and exploitation trade-off, which, if you're not familiar with that, it means that sometimes you have to explore and you have to activate some inputs in order to see how the system responds. But once you have learned how the response it will be, you want to exploit this and optimize the future actions. So with a cancer patient, it's very clear that you don't want to spend too much time trying different therapies because the cancer can grow in the meantime. So you want to minimize the time you spend on exploration and learn as quickly as possible. And this is the dual control problem at the heart.
Amazing. You did a great favor also to myself in explaining this beautifully well. What I found striking, at least in some of the publications that we were mentioning, also related to this thread of research that you're conducting recently, is that you have explicit quantifications now of this trade-off somehow. So where you relate terms like robustness of the system to actually the exploration and exploitation quantified in some ways, obviously. And that I found particularly interesting, something that I personally haven't seen before.
Yeah, so this is what we are trying to do, and obviously we are not the only ones, but I think it's a very rewarding area. where you can take advantage of a lot of past work in control and combine it with modern machine learning literature.
And this is actually maybe a good point where I can make first a clarification. We have talked at length now about dual control, but we didn't say where the term originates. I guess it is very much related to the term adaptive control. And the person who called it that way was Feldbaum, right?
Yes.
So a Soviet scientist. Well, we are, let's say, chronologically now located towards today, and we're nearing the 2 hours mark. I'm thinking that maybe this is actually a good time to transition towards, let's say, the last part of the episode, where I normally ask our guests, what do you think about the future? So final thoughts for the next generation and advice to future students. Since we mentioned that every decade of control has a certain flavor to it, what is the flavor of the next decade?
That's the hardest question, and that's something we will never know until we can look back. But I definitely, as I just indicated, I think there is a lot remaining to be done in the interface between learning and control. Of course, this is something Carl Ostrom could have been saying 50 years back in time. It is true also for AI in general that it has been coming and going, and that doesn't necessarily mean something negative. But I think also, if you look at how people are trying to apply AI in various contexts today, there is a lot of low-hanging fruits that people can pick and progress that can be made. But there are also areas, and I mentioned the cancer treatment as an example, where you cannot afford to just try. You have to think before you act. And this is also true in other areas where we want to apply learning in society. We cannot afford to make too many mistakes. So we had better use the tradition in control, which also is looking for robustness. Use the tradition that we take advantage of physics knowledge and first principles when they are available. And I think this will be very essential. And of course, I'm very, like everyone else, I'm worried now about what's happening in society and how technology and social media is interacting with a reality that cannot tolerate too many mistakes. I think systems theory should play a role also in the understanding of the big picture of how humans interact with climate and how it all goes together. I think our subject has a role to play in the most important questions of our future. John Doyle is pointing to architecture as the key concept. I think he is right. Architecture is really essential. But the most important aspect of that message, I think, is that we should not be afraid of looking into the big picture and see where we can make a difference.
And that is wonderful advice. I have just one last question maybe, and then we can gradually close the episode. The question is, if you were a young student today, it's not about what topic or what sort of investment to make, but more related to if there's something that you wanted to know at that stage that you didn't know and that you think would be important for a student to know today, what would it be?
I think it's important for a young student to get out there to the conferences where you can see what's going on in the field, much broader than what you can see at home or what you have tried so far. And don't be afraid to travel alone because that forces you to meet people that you maybe wouldn't meet when you go with friends only.
I think that is wonderful advice. Also, let's say a broader level, like travel alone also with your research. As you've shown also by example, it led to amazingly creative and original work. Well, I guess then this brings us to the end of this episode. Anders, it's been wonderful to chat with you, and thank you so much for joining us.
Thank you very much for having me.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.